Ever wondered how those scientists and investigative TV shows determine the composition of a sample? Well, one device scientists use is called a mass spectrometer. A mass spectrometer is a device that separates a sample into its different components using electromagnetism. First, the sample is put into a vacuum. Now, this vacuum ensures that when the sample are separated into ions later on, the ions will not react to the environment or the air. Then, the sample is bombarded with high energy electrons. This high energy electrons will ionize the sample. This means that it will either lose an electron or will separate into its ions. Either way, it will end up with a positive Q charge. Then, the sample enters an electric field. This electric field will accelerate the ions due to the potential difference between the positive plate and the negative plate. The next part is for the ions to enter a magnetic field. This magnetic field will bend the ions, and depending on the masses will curve differently. Now, as we can see, these ions did not bend as much. Therefore, these ions are the more massive ones. And these ions that bend more or the most is the less massive ones. Now, the last part of the mass spectrometer is what is called a detector plate. The detector plate converts these information into what is called a mass spectrograph, such as this. Now, in some mass spectrometer, this electric field and the magnetic field are combined together to form a velocity selector. Okay, so we have our ions over here, and when they were bombarded with the high energy electrons, they are focused into this little slit, into a beam, and goes through this slit. Now, this beam then goes through a uniform electric field and a magnetic field. Now, let's look at this for a sec. If we look at our magnets, north and south, we can say that they are in the z-axis. That means it is either going into the page or out of the page, depending on the directions. And when we look at our plates, our positive plate here and their negative plate here, we can say that they are on the x-axis, or that they are going up or down, depending on the direction. Now, as stated earlier, we have our magnetic field on the z-axis. If we look at this, we can say that it's going to the negative z-axis, or it's going into the page. when we use our right hand rule, we use our index finger towards the direction of the particle. We use our middle finger direction of the magnetic field, which would be going in, and our thumb is the magnetic force. If we look at that, we can see that our FB, or our magnetic force, is going up. Now, as stated earlier, we have our electric field on the x-axis. Now, if we look at this, we have our positive plate on the top and our negative plate on the bottom. What this means is that the direction of the electric force would be going down towards the negative x-axis, Fe. And so, the particles that have enough velocity will go through the slit and continue on to the next part of the mass spectrometer. But there are some ions that will be too slow because of their charge, and these ions will be deflected out and will not be recorded into the detector plate. Okay, now this mass spectrometer is set up so that the electric force, Fe, is equal to the magnetic force, Fb. But as you can see, they're on opposite directions. Now, Fe is equal to the charge times the electric field, QE. Hence, this is equal to the magnetic force, which would be Q, V, B, sine theta. Now, sine theta accounts for the angle between the electric field and the magnetic field. In this case, since we know that the magnetic field is going to the z-axis and the electric field is on the x-axis, we know that they are perpendicular, or that theta is equal to 90 degrees. Now, what this means is that the sine of 90 degrees, put in our calculator, is equal to 1. Now that we know this, we can just eliminate the sine theta from our equation, giving us QE is equal to QVB. Q as in the charge, E is the electric field, V is the velocity, and B is the magnetic field. Now, we can see that the Q's are on each side of the equal sign, so we can cancel them out, leaving us with E is equal to the velocity times the magnetic field. Now, if we algebraically manipulate the formula that we have, we can come up with the velocity, or Vs, velocity selected, is equal to the electric field over the magnetic field. Now, this formula is why this is called a velocity selector, because it selects the velocity of the particles that goes through the slit.
Now, we can use this visual to summarize the physics behind a mass spectrometer. First, the ions enter the vacuum. Then they are bombarded with high-energy electrons. And then they enter the electric field and the magnetic field, otherwise known as the velocity selector. Then the ions enter an area with only a magnetic field, bending the path of the ions depending on the mass of the individual particles. As we can see, the bigger ions will bend less than the smaller ions.